Good afternoon, sir, and welcome to the webinar series organized by Parul University. Today we have among us Dr. Satish Shah, Assistant Professor in LD College of Engineering. So, on the behalf of Parul Institute of Engineering and Technology Diploma Studies, Parul University, we welcome you, sir.
Thank you very much. And my thanks to your Parul University Principal, Dr. Ruchi Srivastava, Madam, your Head of the Department, Professor Prabha Modi, Madam, the moderator, what you are doing nowadays is the very good duty, Professor Parth Modi, sir.
Thank you,
And
sir.
my student and currently lecturer at Parul University, Bariya Nitesh, sir.
Yeah.
And all others, those who have helped me a lot for making my presentation visible to all of you. And I think now there is no difficulty, then I can start my presentation.
Of course, sir. Sure.
All right. Thank you very much.
Yeah, okay.
Okay, so let me first tell you that the topic which I have selected today for my presentation is process design of cell and tube heat exchanger. I think most of them, they are the viewers are the students, isn't it?
Yes, correct.
And as Nitesh told, it is from diploma engineering, and most of them they are having the subject of heat transfer.
Yeah, correct, sir.
All right. So keeping that in mind, I have just planned my presentation. I'll try to go as slow as possible. So, but still, if you have any doubt, later on also you can contact me or you can contact your professor and just contact me also later on. So this is like this only, and I will just start it like this. So the screen is visible, I suppose.
Yes.
Isn't it? All
Yes,
right.
sir.
Okay, fine. So now see, basically heat exchanger classification we can do by many ways. So I'm just showing you one of the way. Suppose I can say that recuperative. Recuperative means what? See, basically in heat transfer we have cold and hot fluid which is flowing. So in recuperative the heat transfer, basically there is in between we have metal wall. So suppose we'll take case of cell and tube heat exchanger. One fluid will flow in the cell and other fluid will flow in the tube. So there is in between we have the tube wall. So this type of thing is there. Other type, that is regenerative. Regenerative means what? So we have the same heating surface which is alternatively exposed to hot and cold fluid. So it will first collect the heat and then it will transfer the heat. While the contact will be other side, it is hot air or cold accordingly. This will be normally used in the steel industry. And third type, that is direct contact. So direct contact means both the fluid will come in direct contact. Say if you take the example of say cooling tower, all of you are knowing that in cooling tower what happened, that we have the cooling water which will go to the heat exchanger in the process, and while returning the temperature will be hot, and that we are taking to the cooling tower. So hot cooling water that is entering from the top of the cooling tower, and side by side it is help of induced drop cooling fan, and there is a heat transfer. Basically, there is a heat transfer as well as mass transfer. So it is known as simultaneous heat and mass transfer. So that is also considered as the type of heat exchanger we can say. Now the other type of heat exchanger I will say, suppose we have the flow pattern. It is say counter current flow or co-current flow or parallel flow. All these are the different types of the flow. As per the direction of the hot and cold fluid, will define it accordingly. Similarly, the other types, see general types, we know that we have cell and tube heat exchanger, we have plate type heat exchanger, we have box type of heat exchanger, we have spiral heat exchanger. These type of many heat exchangers are there. But see, what is my focus today is to discuss with you only the cell and tube heat exchanger. It may not be possible to cover all, even may not be cover the only cell and tube heat exchanger also. But still, I will try to cover maximum possible of the process design of cell and tube heat exchanger. So here, if you just see, initially I will just introduce to you what is cell and tube heat exchanger, and then we'll discuss the process design part. So basically, the design code available for the cell and tube heat exchanger for doing process design and mechanical design, that is British Standard BS 3274. Then we have the TIMA standard. All of you must have heard the word TIMA. TIMA means it is Tubular Exchanger Manufacturer Association. This is the association. They have formed the norms for the heat exchanger. And if you follow the norms, then you can very well design your heat exchanger, and after design also you can verify it. So what they have done, they have divided the total design into three different classes. The classes are B, C, and R. What does they indicate? When I'll say class B, what does it mean? Class B means it is for the chemical process service, normal service we say. Then we have the class C, that is for the moderate requirement of the commercial and general process application. And when I will say class R, that is for the petroleum industry. See, it is for the toxic fluid, we can say. Say, for example, benzene, toluene, like these fluids will be using the class R. Now, in all these different classes, they have specified many things that, suppose I will give you one simple example. Suppose, for example, tube seat. We are not going to design tube seat just now, or we are not going to discuss also because it is part of mechanical design. But here they have given the nomenclature for that. Suppose you want to design the tube seat, there is formula available. You can use the formula, and later on, what you can do, you can just verify. They have given the value that, suppose class B, your tube seat thickness should be equal to tube OD. This is your minimum requirement. So suppose you have taken your 19.05 mm tube OD, your tube seat thickness you will take 20 mm. Then suppose I have class R. In class R, they have told that the tube seat thickness will be 2 times the tube OD. It means now if I am using class R, or I am designing my heat exchanger for class R type of fluid, then I have to take my tube seat thickness to be 40 mm if my tube OD is 19.05 mm. This is the basic fundamental of TIMA, and we have to always refer to TIMA for if we want to finalize the mechanical design of the heat exchanger, cell and tube heat exchanger. Okay, now basically we'll discuss, I told you that we'll be discussing the cell and tube heat exchanger, which is most commonly used type of heat transfer equipment in the chemical and allied industries. Any chemical industry you visit, you will find at least 1, 2, or many cell and tube heat exchanger there. So let us say, what are the advantage of that? The configuration gives a large surface area in small volume. In detail, we'll see later on, but just now, you should know this thing, that we have good mechanical layout, good shape for pressure operation. So because we have to maintain some pressure also in the cell or in tube. So this is the best design. Uses well-established fabrication technique. This is very important because see, once you design the equipment, but if fabrication is not proper, then it will not work properly, because safety is also very important and can be constructed from a wide range of material, whatever material you will choose, because see, ultimately we know that our chemical industry is corrosive industry, and you have to select accordingly the material as far as the corrosion is concerned. So that is very important, that the construction should be possible with any type of material. So sometimes suppose we can use only carbon steel material, and sometimes we can use the even SS material or Hastelloy material or any material. That is possible. Even tube seat and part can be even cladded also, that is possible. But see, if you go for plate type heat exchanger, this we don't have possibility, because you cannot fabricate plate from the very simple material like cast iron, cast steel. That is not possible. So you have to definitely go for the material which is very costly. Then it is easily cleaned. Easily cleaned means, see, we have possibility that we have fixed tube heat exchanger and we have floating heat exchanger, we can removable bundle heat exchanger also possible. You can remove it also, or you can do it chemical cleaning also. Everything is possible. All right. So that is all right possible in this case, and the design procedure is also well established. So you can definitely design it, even though you don't have very sophisticated software available with you. You can design it with simple formula also, and we have designed many heat exchanger, and which is working nowadays in the industry also. All right. Okay. Now, so let me just show you the cell and tube heat exchanger, just the figure. So at least you have some idea of the cell and tube heat exchanger. Mostly, I suppose you must be knowing also. So this basically, see, we have the cell. Cell, everybody is knowing it, and inside we have the tubes. These are the tubes, and we have the nozzle for inlet of the cell side fluid, outlet of the cell side fluid. Similarly, inlet of the tube side fluid, outlet of the tube side fluid. These are the nozzles. Then we have the pass partition plate in between. Here, suppose I tube side I have kept the pass partition plate. If it is more than one pass, we have to put the pass partition plate. If it is single pass, it is not required. Then we have the baffles. You can just see the baffles over here in the cell side. I think you must be knowing the purpose of baffle, because see, we want to transfer our fluid this way. This is our flow pattern. Is it all right? Isn't it? I'm just showing you the flow pattern like this with the help of this cursor. This way. All right. So this way there is flow pattern. We have the tube seat on both the end of the tube, and then we have flange also. Then we have the channel, or we can say it is head. So this way, this heat exchanger is there. Now see, now what TEMA has done. Suppose this is the heat exchanger which I am showing you. And if you want to write down as per TEMA, they have specified the front head, rear head, and the cell type. So suppose I will say that AES, where A means it is front head, E means it is type of cell, where we have the single pass only, and S, that is the rear head. This way, they have given the designation to the different front head, rear head, and cell. They have told that suppose F type you are using, F type means it is two pass on cell side. But what we normally don't prefer to use the F type cell. All right, because of the construction limitation. Okay. Now see, we have the two type of basic cell and tube heat exchanger, that is fixed tube design and floating head. I told you that suppose you can even remove the total head, or you can just move also, and accordingly you can adjust the variation. Suppose I have the liquid and which is vaporizing, it is possible that the volume will increase, and to take care of that I can use the floating head type of design. Otherwise I will be normal design, it will be of fixed tube seat heat exchanger, where once I'll be put the bundle, then only I'll be using this heat exchanger, and when I want to clean it, I have to just open everything, but you cannot simply remove only the tube bundle. All right. So we have this type of possibilities there. So as per our requirement, we have to see it. So let us go to the design part of the process design part, and there are various methods available. I'll just tell you, and then we'll be discussing only one method. See, basically we have the Kern method, which is nowadays it has become old method. Because see why it has become old method, because it was not considering the bypass and leakage stream. That was one reason. Second thing, see, if you find Kern, if you refer the book of Kern, it is in FPS unit only. It is not, they have not converted into MTS or SI unit. That is limitation of it. And third thing, they have kept the baffle cut fixed 25%. They have not changed the baffle cut. So we have to keep the provision of changing the baffle cut. We have to take care of the bypass and leakage stream, and everything we are doing in the current method, which is known as the stream analysis method, which is proposed by Tinker. See, Tinker has told that in this, I'll just again go back to the heat exchanger figure. See, here if you see here, when the cell side fluid is moving, cell side fluid, suppose entering here, what we have assumed that it will flow like this. But do you feel that is it possible that 100% fluid will move like this only? No. Why not? Because, see, this is a tube and this is a baffle. And we have the hole in the baffle for the tube to pass. So there will be slight gap will be there. Slight gap means even it will be 0.05 mm to 0.1 mm. That type of gap is also there. Even though the fluid will pass from that also. So whatever we are assuming and we are doing design based on our assumption, that is this type of flow which is known as the B stream according to the Tinker model. But it will not happen all the time. All right, so this is our stream analysis and we'll be doing this. Then we have the Bell and Delvare method. Even see whatever small gap between the tube and baffle and cell leakage, that is also taken into account by the Bell and Delvare method. But by experience, we have found out that even though you will not go for Bell and Delvare method, it will not have any problem because we have done the analysis using Tinker's model that what is the effect on heat transfer and what is the effect on the pressure drop. All right. Okay. Now see, as far as the construction detail is concerned, we have the tube. What is the dimension of the tube? General range, if you see, it is 5 by 8 inch to 2 inch. That is 16 mm to 50 mm. See, many times you will see that we are using FPS unit as well as MTS unit both because we are habituated to use FPS unit, isn't it? So we have to use both. But nowadays it is available. So sometime what will happen, sometime I will tell you that you will be using 6 feet tube. So immediately you have in your mind that you will be converting this 6 feet exactly into mm. And the figure which you are getting will be not matching with our normal 2000 mm or 1500 mm or 4000 mm, this type of MTS length. But it is available. All right. Now, small diameter, that is 5 by 8 is to 1 inch, which is normally preferred. And most of the time we are using 3 by 4 inch or 5 by 8 inch. That is 19.05 mm tube body or 15.875 mm tube body. This is what we normally use it. Then larger tubes for heavily fouling fluids. See, basically the fluid has some nature that it will foul the heat exchanger. Fouling means it will have scale formation. So when there is scale formation is more, we have to take the higher size of the diameter of the tube. So at least scale formation will be less. We should maintain better velocity, higher velocity for the tube side, but there is limitation that we cannot exceed some value because otherwise it will erode the tube. So keeping that in mind, we will just verify. Otherwise, we have to make some other provision also. Then we have the different material of construction possible. Code is also we can use. And then preferred length also, I have mentioned that it is 6 feet, 8 feet, 12 feet, 16 feet, 20 feet like this. Or you can use in mm, 5000 mm, 6000 mm like this also, that is possible. And then optimum tube length to cell diameter ratio, that is in the range of 5 to 10. And I told you that we'll be using 19.05 mm, that is 3 by 4 inch, that is the tube body. For whenever we want to start our design, we'll start with this. And later on, if we found that, okay, this diameter we want to change it, we'll change it. This is what is normal practice. Now see, basically, tube can be arranged in different pitch. It can be arranged in triangular pitch. So you can just see here the triangular pitch. This is equilateral triangle. This is tube body, and whatever is shown here is tube pitch, that is generally 1.25 times the tube body. So if your tube OD is 19.05 mm, then your tube pitch will be 23.81 mm. This is general, I am telling you. You can just vary also later on. Okay. Because if you want to adjust your pressure drop, sometime we have to adjust it. But what is normal practice is you keep it 1.25 and accordingly they have given all dimension and everything. See, this is square pitch. You can just see the square here and where everywhere the angle is 90. So it will look very simple and calculation will also be very simple. And third is rotated square. So basically it is just rotation only. Okay. Now the construction details. See, cells should be close fit to the tube bundle to reduce the bypassing. Basically, whenever you want to do design, what you will do? You will first calculate the bundle diameter. And after calculation of bundle diameter, you will fix up the cell diameter. So suppose my bundle diameter is 294 mm, for example. Then what I will do? I will take my cell diameter to be 300 mm. Okay, this is I am telling you rough figure 300 mm. Later on you have to verify with the standard available pipe size. What do I mean by this? 300 means roughly you can say that it is 12 inch. So you have to now refer the pipe table. For 12 inch pipe, what is the OD? What is the ID? Everything for suppose you are taking say 40 schedule. 40 schedule. Accordingly, what is the dimension of all this that you have to verify and whether our number of tube, whatever we have taken, whether it is fitting in this or not, that you have to verify. All right. Then cell bundle clearance will depend on the type of heat exchanger. I told you that suppose you want to remove the bundle, then you have to keep slightly more clearance. And when you want to fix tube heat exchanger, in that case, you can keep slightly lower clearance. That is okay. But remember one thing, whatever clearance you are keeping, we are taking care even that fluid may not pass from that particular point in more quantity. And for that, we are providing the sealing strips. Okay. Now here they have shown the bundle diameter and cell inside diameter. So this, okay, as per the type of heat exchanger, it will vary. All right. Now, as I told you that what is important for us is the first step, that is always to calculate the bundle diameter. How will calculate the bundle diameter? The formula is dB is equal to DO NT by K1 whole raised to 1 by N1. All right. Can you see this formula, all of you? Okay. So what you can do? You can just note down if you want to note down. Otherwise, it is available in the standard book. dB is equal to DO into NT by K1 whole raised to 1 by N1. Here dB, that is your bundle diameter. That is, suppose I will take in mm. If I will take DO in mm, because there is only two sides. If you see, we have only dB and DO. So both should have the same unit. Other everything is unitless. So this DO, that is tube outer diameter in mm. NT, that is the number of tubes. And K1 and N1, they are the constant. And for that, the table is given over here. See, this is the table for triangular pitch. And this is the table for the square pitch. So you can just note down N1 and K1 over here. This is pass 1, pass 2, pass 4, pass 6, pass 8. Tube side passes. And accordingly, they have given the values of N1 and K1. And if you will use square pitch, for that also, N1 and K1 value is given like this. If time permit, I will show you the example also. But otherwise, you should keep in mind that you should use this formula to find out the bundle diameter. So once the bundle diameter is finalized, you can immediately finalize the cell diameter. Now see, on the cell side, we are using baffles. You must be knowing that. What is the purpose of using baffle? The purpose is to direct the fluid stream across the tubes to increase the fluid velocity to improve the rate of heat transfer. Most commonly used baffle is the single segmental baffle. Most commonly used baffle is the single segmental baffle. See, there is double segmental baffle, triple segmental baffle, everything is possible. See, what do I mean by single segmental? See, this is basically the total baffle, 100% full baffle if I am saying. It is as in the form of the circle. Now, I am just cutting 25% of that from one side and here also. These two baffle I'll be putting one like this, other I will put like this. So I am in a position to maintain my flow of the cell side fluid. So this is single segmental baffle. But suppose my pressure drop is more, I'll be using double segmental baffle also. So in double segmental baffle, what will happen? Instead of this one cut, I have to cut from both the side. So when I'll cut from both the side, the center portion will remain open. So that central portion I'll be putting as second baffle. And third time again I'll be putting like this. So this way it is known as double segmental baffle. All right. So this way the flow will follow the cell side pattern. Now, see, it is shown here this way, the flow pattern. And the baffle, regarding baffle cut, I told you that as per ton they have fixed 25%, but we can change it and we are keeping sometime varying from 20% to 45%. But according to them, that the optimum baffle cut is 20 to 25%, but that we have to verify based on the pressure drop. Now see, whenever you want to design cell into heat exchanger, you should always, or any heat exchanger, you should always keep in mind that this is the general equation, very important equation you will be using for design purpose. What is this? Q is equal to UA delta Tm. What is Q? Q, that is the quantity of heat transferred. U, that is overall heat transfer coefficient. A, that is area of the heat transfer, and delta Tm, that is the LMTD. It is log mean temperature difference, or we say mean temperature difference because we are applying correction factor for LMTD. So it is Q is equal to UA delta Tm. Now see, basically what is Q? Quantity of heat transferred. How you can calculate quantity of heat transferred? It is mCp delta T, or it is m into lambda. When there is no phase change, the heat load you can calculate by just mere formula, that is Q is equal to mCp delta T. And when there is phase change, you will calculate Q is equal to m into lambda. Now, you will calculate U also. For calculation of U, what you have to do, that we'll discuss in the next slide. Before that, I'll tell you, you can calculate the LMTD also. That is log mean temperature difference. So what you can do, see, this is the formula for overall heat transfer coefficient. This is the formula for overall heat transfer coefficient. What is the formula? It is 1 upon UO, that is equal to 1 upon HO. HO, that is outside heat transfer coefficient, or it is cell side heat transfer coefficient. 1 upon HOD, that is dirt coefficient for the outside. Then DO ln DO by DI upon twice KW. What is this? It is the resistance provided by the tube metal. So it is DO ln DO by DI upon twice KW, where KW, that is the thermal conductivity of tube wall. Then DO upon DI into 1 upon HID. HID means it is dirt coefficient inside. And then DO upon DI into 1 upon HI. HI, that is the inside heat transfer coefficient. So see, if you want to know U0 or UO, overall heat transfer coefficient, you should calculate HO, you should calculate HI, and you should know the value of HOD, HID, and KW. All right. So if you know all these things, you can calculate overall heat transfer coefficient and after overall heat transfer coefficient, you will calculate the area required. Okay, because our formula is Q is equal to UA delta Tm. Now see, I told you that we have HO and HI. They are known as the individual film coefficient. Now this individual coefficient depend on the what is already you are studying, conduction, convection, radiation, everything. Then second is physical property of the fluid, because I told you that when you want to calculate Q, you have to calculate MCP delta T. So CP, that is specific heat of the fluid. Similarly, later on you will know that we have to calculate Reynolds number, Prandtl number, everything, where we need many properties of this fluid. Then what is important is the flow rate of the fluid. And then what is important is the layout, physical layout of the heat exchanger or heat transfer surface. All right. So all these things will give you the individual film coefficient. And see here, I told you that whenever you want to start your design, what you have to do, because see, we want to calculate area. For calculation of HI and HO also, you need some basic heat exchanger. So from where you will get it? So for that, what you have to do? You have to assume value of U. Again, I'll just go to that slide where I have mentioned this Q is equal to UA delta Tm. So here that U, you have to assume. And how to assume? For that, they have given us some table or some feeder. You can use that feeder, but later on by experience also you can write down or assume some different value. But remember one thing, when there is no no phase change, the value of U will be low, but when there is phase change, that is condensation or vaporization, the value of U will be more. So if you want to start with no phase change, you have to assume low value. Low means 500, 600, 700 kilocalorie per hour meters per degree Celsius or watt per meters per degree Celsius. This is what the value of U you will assume. Q you will calculate, delta Tm you will calculate, and based on that you will calculate the area, which is known as the area provided. So this is the table for assumption of U value. Here also you can use this table also for the value of U. Now see, we have to also assume the fouling factor, or it is known as dirt coefficient. And it is difficult to predict, but we have to assume some value, reasonably good value. All right. So when you assume the value in terms of coefficient, it will be like this, 3000, 5000, 6000, like this. So please remember, when you write down this formula, what you write down here, if it is 3000, 4000, 5000, then write down like this. But if it is 0.0003, then that value you have to write down in place of 1 upon HO directly. Don't put that value as HO. Is it clear to you? Sorry, HOD or HID. Okay. So this is where you can assume the value of the dirt coefficient. So again, we will reach to this. I told you that you have to assume you have to calculate delta Tm, that is the LMTD value. How you will calculate LMTD? If it is completely counter-current flow, this is a formula. You can calculate log mean temperature difference by this formula, where capital T1 and T2, that is the hot fluid inlet and outlet temperature, and small T1 and T2, that is the cold fluid inlet and outlet temperature. So you can straight away calculate this using delta T1 minus delta T2 upon ln of delta T1 upon delta T2. This is the calculation of LMTD that you must be knowing also. Okay. So when we have completely counter-current flow, then this T1 will go to T2 and this T1 will go to T2 like this, and you will calculate LMTD accordingly. But see, every time it may not be possible. Why not possible? Because if I have, suppose, 2 pass, what will happen when I have 2 pass? This T2, what I have written over here, that will come over here. That will come over here. And whatever I have made assumption, that will go wrong. So in that case, I have to apply the correction factor. See, you can see like this. We have this way 1, 2 heat exchanger. T1 and T2 will be on this side. Cell side T1 and T2 will be like this. And in this type of case, you have to apply the correction factor. So how to apply the correction factor? For that, we have to calculate value of R and S. Value of R and value of S. And that value you have to put in the chart, which will give you value of Ft. I am just showing you that chart also. It is like this. See, these are the different value of R. In the figure you see, and we have the value of S, and you will get value of Ft. So you can multiply that delta Tm value, LMTD value, by correction factor, and you will get delta Tm. Okay. Now see, before starting the design, we have to, suppose somebody will tell you that I want to do the process design of cell and tube heat exchanger, and for that I have some process fluid. I want to heat it or cool it, whatever it is. So immediately you should take decision that which fluid you will be putting on which side. All right. So there are various criteria. I'll tell you only one criteria and then we'll go further. So suppose corrosion. Corrosion means if the fluid is corrosive, we'll prefer to put on the tube side. Why tube side? Because if you put on the cell side, it will corrode cell and tube both. Isn't it? Because tube is also in contact with the cell side fluid from outside. But if you put on in the tube side, it will be only corroding the tubes, or you have to keep the material of tubes in such a way that it will not corrode it. Is it clear to you? So similar, all these criteria you have to verify. Then there are certain limitation or velocity thing they have told us that, see, suppose we have tube side fluid. Then suppose it is water. Mostly we'll be using water if it is used as a cooling purpose on the tube side only. In that case, it is better that you maintain your velocity of the tube side fluid between 1.5 to 2.5 meter per second. General process fluid on tube side, you keep the velocity 1 to 2 meter per second. All right. Similarly, cell side fluid will keep velocity of 0.3 to 1 meter per second. Now see, this velocity, you should take care that, remember one thing, when you increase your velocity, your heat transfer coefficient will increase. That is advantage. But at the same time, your pressure drop will also increase. So that you have to take care. So it should not exceed certain value. At the same time, if it is very low pressure drop, it means that there are all the chances of increasing this velocity by increasing, if it is on tube side, by increasing the number of passes or reducing the tube size or anything. Is it clear to you? If it is on cell side, how you can adjust? You can adjust by making the baffle spacing. If you reduce it, the velocity will increase. If you increase it, the velocity will decrease. So what is important for us is the pressure drop which is available to us on the cell side as well as on the tube side, and accordingly you have to design your heat exchanger. So once your design is over, you should always check the pressure drop and then only you should say that, okay, my design is complete. Till that time, you cannot say that my design is complete. Now see, tube side heat transfer coefficient. How to calculate the tube side heat transfer coefficient? There is a standard formula available which is known as Sider-Tite equation, or it is known as Ditus-Boelter equation. That is, say, the best thing that we have, Nu is equal to C Re raised to 0.8, PR raised to 0.33, mu by mu W raised to 0.14. In which, what is Nu? Nusselt number, HD by K. What is Re? Re, that is Reynolds number. It is du rho by mu. What is PR? Prandtl number. It is Cp mu by K. And what is mu by mu W raised to 0.14? So basically, when there is viscosity variation at wall and in the bulk, if it is very much, then we have to consider this factor. Otherwise, for our normal design, we will not consider this factor and we take this to be unity. So your formula will be only this, and here C is a constant. So what is the value of C you will take? It is 0.01 for the gases, 0.023 for the low viscosity liquid, and 0.027 for the viscous liquid. So you can write down this formula, and in this formula, Reynolds number when you want to find out, it is du rho by mu. Now suppose it is tube side fluid, you will take tube ID. But if it is cell side fluid, you have to take equivalent diameter. Then UT, that is velocity, rho, that is density, and mu, that is viscosity. Please remember, Reynolds number should be dimensionless. So you cannot use as it is whatever value is given to you and you just substitute the value, and whatever Reynolds number you are getting, you accept it. That is not acceptable. You have to make sure that it becomes dimensionless. All right. So suppose you are using an MTS system, you have to take rho in kg per meter cube, you have to take UT in meter per second, DE you have to take in meter, mu, that is viscosity, you have to take in kg per meter into second. If you take like this, it will become dimensionless. Similarly, Nusselt number HD by K, where H is heat transfer coefficient, the unit will be kilocalorie per hour meter square degree Celsius or watt per meter square Kelvin. And Kf, that is the thermal conductivity. Similarly, Prandtl number, that is Cp mu by K, where Cp is specific heat, mu is viscosity, and K is thermal conductivity. All right, so you can calculate the tube side heat transfer coefficient using this formula. There are some other formulas also possible. You can calculate this formula whenever we have laminar flow. But remember, most of the time, when we are designing the heat exchanger in the industry, we have Reynolds number greater than 4000 only. And there, the what we are getting? Turbulent flow. All right. Sometimes we are getting Reynolds number even in lakhs also. All right. Then see, they have given the chart also for JH. You can use that chart also to find out JH value from the Reynolds number, and you can use it for calculation of heat transfer coefficient. And that is applicable to any type of flow, whether it is laminar or turbulent. So this is the chart available to you. You can use, this is known as tube side heat transfer factor, and you can use this chart for calculation of the JH factor. And that JH factor you can substitute in the formula and you will calculate the heat transfer coefficient. Now see, I told you that most of the time we have water, which is used as a tube side fluid. If it is water, you need not worry much because we have the ready-made formula which is applicable only to water. Remember, only to water. And because it is empirical formula, you have to use the unit carefully. Say this, what is this formula? 4200 into bracket 1.35 plus 0.02 T into UT raised to 0.8 upon DI raised to 0.2. So HI, that is the inside heat transfer coefficient, watt per meter square Celsius. T, that is the, now see, T, that is the water temperature, that is average water temperature in degrees Celsius. So suppose my cooling water temperature is changed from 32 to 36. I have to take value of T to be 34 degree. UT, that is the water velocity which you have to take in meter per second. And DT, that is the DI, that is tube inside diameter. So if you know the tube body and if you know the gauge of the tube, you will calculate the tube thickness, tube ID, that is tube body minus 2 times the tube wall thickness. So I will give you one example. Suppose I have tube body of 19.05 mm and my tube gauge is 16 BWG. It means my thickness is 1.65 mm. So I can find out tube ID, that is equal to 19.05 minus 2 times 1.65. All right. So that will tell me the value of the ID of the tube. Similarly, you can calculate the pressure drop on the tube side also using this formula. What is the pressure drop formula? Delta PT is equal to NP into 8JF into L upon DI into mu by mu W raised to minus M plus 2.5 bracket complete rho UT square by 2. What is this, all this term that I will explain you immediately? What is delta PT? It is the tube side pressure drop in unit of Newton per meter square. What is NP? Number of tube side passes. What is JF? Similar to JH, I have the ready-made figure available for JF that I have to use, that I will show you after this. L is tube length, DI that is tube ID, and M that is the factor. For 0.25 for the laminar flow, and for turbulent fluid the value is 0.14. Rho that is density of the fluid, UT that is velocity of the fluid, and like this you can find out the tube side pressure drop. Remember, if we have cooling water, generally the tube side available pressure drop is 80 kilopascal. Generally the tube side pressure drop available is 80 kilopascal. See, when I am saying in Newton per meter square, it is pascal. You have to divide by 1000 and you will be converting into kilopascal. So this is the value of JF. You can just calculate the Reynolds number and you will be calculating the JF figure. Now see, cell side heat transfer coefficient, I will be only telling you the Kern method. See, basically what you can do, you can calculate. I don't think that time will permit to solve the problem, but I will, whatever PPT I have sent everything, so you can collect from the organizer for all these things. So cell side pressure drop, design when you want to do heat transfer coefficient calculation, you start with calculation of AS. How you calculate AS? That is PT minus DO into DS into LB upon PT. See, basically how this has come. This PT minus DO, that is the clearance, and DS by PT, that is the number of clearance available at the center, and LB, that is the baffle spacing. So that will give you AS value. Once you calculate AS value, then you will calculate GS, that is equal to WS by AS. WS, that is the mass flow rate, divided by AS, so it will give you mass velocity. And you will calculate US, that is GS by rho, that is the velocity of cell side fluid. After this, you have to calculate the equivalent diameter. How to calculate equivalent diameter? Equivalent diameter is 4 into cross-section area upon wetted perimeter. Equivalent diameter, that is equal to 4 into hydraulic radius, or it is 4 into cross-section area upon wetted perimeter. So if we have the square pitch, the formula will be something like this. And if we have the triangular pitch, the formula will be like this. Okay. Now you calculate the Reynolds number. See, I told you that it is dE U rho by mu, or it is dE into GS by mu. Equivalent diameter you take. GS is mass velocity and mu is viscosity. And you can use this formula, which is similar to the earlier, only difference is Nu is equal to JH into RE into PR is to 1 by 3. So this JH, that is cell side heat transfer factor, that is available in the chart that I will show you now. This is the chart available. So you can use this chart, find out value of JH, find out the heat transfer coefficient. So now you can calculate the pressure drop also using this formula, that delta PS is equal to 8 JF into DS by DE into L by LB rho U square by 2 into mu by mu W raised to minus 0.14. So here also you can find out JF using this chart. So we have the ready-made chart available. you can use it. All right. So now see, let me just summarize the thing, because I don't think that I can take problem. Otherwise, I was thinking to take one problem, but it is now very difficult to complete the problem. So I will just summarize the thing. Whenever you want to start the design, cell and tube heat exchanger process design, what is important thing you should do? The first important thing, you should assume the value of U. Assume the value of U. Now, once you assume the value of U, before that, even we start like this, that you calculate U, Q. Q is equal to MCB delta T or M into lambda. Once you calculate U, calculate LMTD, that is delta TM. If something is missing, you can just make the balance and calculate delta TM. Then you assume value of U and calculate area provided. Once you calculate area provided, that is pi DOL into number of tubes. It is pi DOL into number of tubes. So you will calculate or assume DO and L and calculate number of tubes. Once this is known, you calculate the bundle diameter. Once you calculate bundle diameter, calculate the cell diameter. And then you assume the Baffles. Baffle is normally between 20 to 100% of the cell ID. So that you take Baffle spacing, type of Baffle, and then you go for design of the inside heat transfer coefficient. The calculation I have shown you, if it is water, you are lucky and you can use direct formula of HI is equal to 4200 formula. And then you calculate cell side heat transfer coefficient. Once you calculate that, you go for the overall heat transfer coefficient. The formula is, I already have told you, it is 1 upon U is equal to 1 upon HO plus 1 upon HOD plus 1 upon HI into DO by DI plus 1 upon HID into DO by DI plus DOL and DO by DI upon twice KW. If you do this, you will get overall heat transfer coefficient, dirty. Calculate the area required, because now you have other values available with you, that is Q and delta TM. And then you calculate the area required. From that you compare with the area provided. If your area required is less than the area provided, you will be happy. Then you check the pressure drop, and if you find that your pressure drop is also okay, then you are happy to say that, okay, my design is complete. But remember, it will, whatever I have just told you, it will not so simple like this, but you have to do lot of trial and error method to reach to the final answer. All right. So I think I have completed the process design part. Any query, now you can ask me.
Okay, sir.
Yeah.
I did not receive any questions from viewers right now because it is online on Facebook.
Achha, okay. But you from your faculty also, if somebody want to ask anything.
Yes. No, sir. I have no doubt right now.
Yeah.
So, sir, it was very informative session, and I think many doubts of the students or viewers have been cleared regarding the design of heat exchangers and regarding heat exchanger. So, on behalf of Parul University, we thank you, sir, for giving us your valuable time.
Okay, thank you very much.
Yes,
thanks a lot.
Yeah, yes.
In future also, if any need is arise, you can definitely contact me, and I am here to help you. All right.
Yeah. And sir, कोई doubt होगा तो मैं
Sure, definitely sure. And I am very much thankful to all your managerial team as well as your principal, your head of the department, and everybody. Okay.
Yeah. So once again, sir, thank you, sir.
Yeah, thanks. Bye.
Bye.